Assalamu alaikum students. I hope you are doing well. In today's lecture, we'll go through chapter on Boolean Logic, which is a part of paper 2 for IGCSE Computer Science students. We'll go through the theoretical concepts related to the Boolean Logic chapter with the help of different examples in this lecture. And in the next lecture, we'll go through some of the past papers of IGCSE related to the topic of Boolean logic. Fine. So the objectives that we will meet after today's lecture are the following. First of all, we'll go through 6 logic gates which are a part of your curriculum: NOT gate, AND gate, OR gate, NAND, NOR, and XOR gates. And after this, we'll see 3 very important but related concepts, including logic circuits, logic expressions, and their truth table. We'll see 3 related concepts, including logic circuits, logic expressions, and their truth tables. Fine. And we will see that these 3 concepts, logic circuits, logic expression, and truth tables, these can be given or can be asked in different scenarios. For instance, sometimes you may be given some logic circuit and you're asked to draw a truth table from that logic circuit or find out its logic expression. Similarly, some other time you may be given logic expression and you are supposed to find out its logic circuit or truth table. And still, some other times you may be given the truth table of some circuit and you are required to find out its logic expression or draw its logic circuit. Fine. So these are the 3 different scenarios where these 3 concepts may be asked. Fine. And sometimes you may be given the problem statement, and from problem statement you may be asked to draw the truth table or its logic expression or logic circuit. So the agenda of today's lecture is to cover all these things. Fine. And in the next lecture, we'll go through some of the past papers, fine, related to this topic of Boolean logic. Fine. So let's say we start logic gates. Logic gate is basically the basic building block for any circuit that take either single input or multiple inputs, but produces always a single output. Logic gate, whatever its type is, it either takes single input or multiple inputs, but produces always a single output. And based upon certain rule that we will discuss when we go through different types of logic gates, fine. And after covering logic gates, we'll see that we'll connect various logic gates and combine them to form different logic circuits, which can perform various functions like addition of numbers or subtraction of numbers or multiplying them and so on. The logic gates which are included in your course are these 6 logic gates. Out of these 6 logic gates, the NOT gate is a single input, single output gate. The rest are having multiple inputs. Fine. So we'll cover these one by one. NOT gate, AND gate, OR gate, NAND gate, XOR gate, and NOR gate. Fine. We'll see the behavior of logic gate, or later on even the logic circuit, with the help of a table that is called as the truth table. Most of the logic gates that we'll cover in this will have either single input, which is particularly in the case of a NOT gate only, or multiple inputs. And specifically in your text, 2 input gates are used. Fine. And we will see that for logic circuits, which will be comprised of from various gates, those can have more than 2 inputs. For instance, we'll see different examples of logic circuits where they can have 3 inputs, for instance. In that case, we will see there will be 8 possible input combinations. And if for some circuit there are 4 inputs, then in that case, there will be 16 input combinations and so on. So before starting the logic gates, we can see how can we write down various combinations. For instance, if we have 2 inputs, either for some gate or for some logic circuit, if we are having 2 inputs, let's say labeled as A and B, then since we can apply only the binary inputs, so with 2 inputs, we are having 4 possible combinations: 0, 0, or 0, 1, or 1, 0, or 1, 1. With 2 bits, we are having 4 possible combinations: 0, 0, 0, 1, 1, 0, or 1, 1. Similarly, if for some circuit we are having 3 inputs, then the possible input combinations that we will apply while designing the truth table will be 8: 0, 0, 0, 0, 0, 1 till 1, 1, 1. You can remember these combinations like this, that for the first rightmost column, you write 0, 1, 0, 1, 0, 1, 0, 1. Then for the next column, 2 zeros followed by 2 ones, then 2 zeros, 2 ones. And for the still next column, we are having 4 zeros and then 4 ones. Fine. So in this way, you can easily remember 8 possible combinations in a nice arranged way. Fine. So we had seen that if we have 2 input combinations or 2 inputs, for that we have 4 combinations. It means 2 raised to 2 is 4. Similarly, if for some circuit we are having 3 inputs, so while making its truth table, we have to write down 8 possible combinations shown in this table. And this is 2 raised to 3, which is 8. So if similarly somewhere there are 4 inputs, so for that we can make 16 possible input combinations, the truth table, and so on. So let's say we talk about the first gate, which is a NOT gate, for instance. NOT gate, which is we also call as the inverter, that is the gate with 1 input and 1 output, is the gate having single input and 1 output. its symbol is this triangle followed by a small circle at the output. This is the input, single input, and this is the output, single output. So for every gate, you need to know one is its symbol, other one is its logic expression, and the third thing is the truth table. I mean the behavior of that particular gate. Fine. So for instance, this is the symbol for NOT gate. This is the input. Let's say input is A, and this is the output. Let's say output is represented by X. So the logic expression for this NOT gate is, you can write down it like this: NOT of A. A is the input, output which is labeled as X, it is NOT of A. This is the logic expression for this particular gate. Sometimes you may use the Boolean expression for this as well, and that is written down like A prime. This is the Boolean expression for this gate. This is the logic expression for the NOT gate. But in most of the books, the logic expression is used. Fine. So truth table is, you have to draw all input possible combinations. Since input is just one input labeled as A, so for single input combinations are 2 raised to 1, just two combinations, 0 or 1. Fine. And the behavior of this NOT gate is that it just inverts whatever you apply at its input. Remember these terminologies. 0, we also call it as low. Sometimes we call it as a false, or sometimes we call it as off. On the other hand, 1, we call it as either high or true or on. So these are the various terminologies that you will use. The principle of NOT gate is just it inverts whatever you apply. I mean, if you apply 0 at its input, it will give you 1 as output, and you have to apply 1 at its input, it will give you 0 as output. That's it. This is the behavior of a NOT gate, and that behavior is shown with the help of a table which is called as the truth table. Fine. So you remember 3 things for every gate: its symbol, its logic expression, and its truth table. That's it. Let's move to the next, and that is AND gate. AND gate, its symbol is like this: 2 input AND gate. These are the inputs. Fine. The symbol for AND gate, this is output. So let's say inputs are A and B. The inputs are A and B. Then the logic expression for its output is represented like this: first input A, the second input which is B, and it is coupled through AND. So A and B. This is the logic expression for this AND gate. Fine. A and B. The Boolean expression for the same is, it is A dot B, or sometimes just written down AB. Fine. So this is the Boolean expression. Next, we have to see the truth table for this AND gate. First of all, you have to draw all possible input combinations. So you know, since there are 2 inputs, so we have 2 raised to 4 input combinations. You already know inputs A and B. So 4 possible combinations are 0, 0, 0, 1, 1, 0, and 1, 1. And the behavior of this AND gate is that it gives output 1 when both of its inputs are 1. It gives output 1 when both of its inputs are 1. Otherwise, it generates output 0. So this is as far as the working principle of an AND gate is concerned. Fine. So it is written down here that for a 2-input AND gate, output, let's say it is labeled as X, it is high only when both of its inputs are high. I mean, when both of its inputs are 1. Otherwise, output is low. So we had shown this with the help of this truth table. Sometimes you may be asked a question like this, that you may be given this truth table and you are asked, what gate does this behavior represent? So your answer will be just AND gate. And that's it. Fine. Let's move further. Next is OR gate. Its symbol is this. These are the inputs. And this is the output. And the logic expression that we can write down for this OR gate is the first input, A, the second input, B, and in between OR. So A or B, A or B, that's it. However, if you are interested in writing down its Boolean expression, it is written down like this, A or B. Fine. So the truth table for this, again, since inputs are 2, so 2 is 2 is 4 input combinations. A, B are the labels assigned to inputs. So 4 combinations are 0, 0, 0, 1, 1, 0, and 1, 1. Output is, for instance, labeled with X. So the principle of an OR gate is such that its output is low or 0 when both of its inputs are zeros. Output of an OR gate is low when both of its inputs are zeros. It means otherwise its output is 1. I mean, if either of the input is 1, the output is 1. This is as far as the truth table of an OR gate is concerned. Fine. And it is written down over here that for a 2-input OR gate, output is low only when both of its inputs are low. Output is low only when both of its inputs are low. Otherwise, output is high. I hope it is clear. Next is NAND gate. And its symbol is shown here. Symbol like AND followed by a small circle at the output. These are the inputs, let's say A and B. These are the inputs. This is the output. Let's say we call it as X. And its logic expression is written down like this. A, NAND, since it is NAND, and then the second input, which is B. So A, first input, second input B, and those are coupled with NAND. Fine. So output expression, logic expression for NAND is A, NAND B. Now we can see its truth table. The 2 inputs, 4 combinations for A and B. So NAND gate, its behavior is considered as AND followed by NOT. The behavior of NAND gate is considered as AND followed by NOT. So it means, for instance, if inputs are 0, 0, so 0 into 0, 0, and then we have to invert it. 0 into 0, 0, invert here, then it is 1. 0 into 1, 0, and then its inversion is 1. 1 into 0 is 0, then invert it, 1. 1 into 1 is 1, and then we invert it, gets 0. So you can summarize the behavior of a NAND gate as that its output is 0 when all of its inputs are 1. But for two input NAND gate, you can say its output is 0 when both of its inputs are 1. Otherwise, output is true. I hope it is clear. Next, NOR gate. The symbol of NOR gate is this. This is the symbol of OR followed by a small circle at the output. Let's say these are the inputs. Output is labeled as, for instance, X. Fine. So its expression is, logic expression for NOR gate is written down like this. The first input, which is A, then NOR, and then the second input, which is, for instance, B. So X, which is this, it is A NOR B. Let's see its truth table. NOR gate is considered as an OR gate followed by a NOT gate. NOR gate is considered as OR followed by NOT. Fine. So it means to build its truth table, let's say two inputs A and B. So four possible input combinations 0, 0, 0, 1, 1, 0, and 1, 1. So output is, first you have to OR them followed by inversion. So 0 OR with 0, 0, and then we have to invert it. So output is 1. 0 OR with 1 is 1, and then you have to invert it. It will be 0. 1 OR with 0 is 1, and then invert it, 0. 1 OR with 1 is 1, and then invert it to 0. So you can see that the output of a NOR gate is 1 when both of its inputs are zeros. Output of a NOR gate is 1 when both of its inputs are zeros. Otherwise, output is going to be 0. That's it. I hope it is clear. Next, another gate, which is XOR or exclusive OR gate. Its symbol is like this, OR, and along with that, small arc. Fine. So inputs are, let's say, A and B. Output is, for instance, X. So first of all, logic expression for this exclusive OR gate is first input, which is A, then XOR, followed by the second input, which is B. So A XOR B. This is how you write down its logic expression. And next we'll see its truth table. So for two inputs, A and B, we're having four input combinations 0, 0, 0, 1, 1, 0, and 1, 1. The behavior of the exclusive OR gate is such that its output is true when both of its inputs are different. Its output is true when both of its inputs are different. I mean, if A is 0 and B is 1, or if A is 1 and B is 0, when both of its inputs are different, its output is going to be true. Otherwise, its output is going to be false. So you can see that for an exclusive OR gate, output is high when either A is low, and B is high, or when A is high and B is low. And otherwise, I mean, when both are either high or low, the output is going to be false. When both are either low or high, the output is going to be false. That's it. This is as far as the truth table for exclusive OR gate is concerned. This is as far as the truth table for exclusive OR gate is concerned. Fine. Next, we will see logic circuits, their truth tables, and corresponding logic expressions. And as we had seen earlier, that these are three related concepts and may be asked in different scenarios. So let's talk about these different scenarios. For instance, you may be given some logic circuit and asked to draw either the truth table or find out its logic expression. So let's say we see this. So for instance, you are given some example where you are shown some logic circuit where A and B are inputs. In fact, these things will not be given to you. Fine. You will be given inputs, then different gates connected in certain fashion, and the output expression, let's say, labeled as X or F or whatever. And you are asked to, let's say, write down logic expression first, followed by the truth table. Fine. So as far as the logic expression is concerned, what you have to do is, for instance, this input is A, and it is being passed through a NOT gate. Fine. So its output, its logic expression will be like NOT and whatever is the input, which is A. Fine. So you can easily write down the expression for this single gate, which is NOT of A. Next, you can find out the logic expression for this AND gate, having two inputs, and one input is labeled as NOT of A, second input is labeled as B. So you know the expression for AND gate is what? First input, which is NOT of A, then AND in between, and then the second input, which is, let's say, B. That's it. Similarly, you do it for this AND gate, where one input is A and second input is B. So its expression will be A, the first input, and then the second input, which is B. So this is the logic expression for this particular gate. And finally, you may call these as, let's say, P, and this as Q, for instance, if you like. And then the output of this OR gate, which is labeled as X, and two inputs coming to this OR gate. One is this, for instance, P, and second one is this, which is Q. So X is just P or Q. Replace P with this sub-expression and Q with this sub-expression. So X is P, which is all this, not of A and B, and then this OR, and this A and B, this sub expression. Find A, then and this B. So this is the logic expression for this particular logic circuit. Fine. So very simple. You may be asked to write down the logic expression for this particular circuit. So I had shown it over here. Fine. Next, if you are required to draw the truth table as well, fine. So you know the inputs are A and B. So two inputs. First of all, for the truth table, you write down the inputs. With two inputs, you have four possible combinations: 0, 0, 0, 1, 1, 0, 1, 1. Then what you will do is, let's say you see that if somewhere in the circuit some not is required, not of some input variable, first of all, you do what? You draw the column for that. So we have drawn the column for not of A. That is very simple. You just invert the column of A to get not of A. So for 0, it is 1. For 0, it is 1. For 1, it is 0. And for 1, it is 0. Fine. So you build this column for not of A. Then you can build the expression for P, for instance, which is not of A and B. Not of A and B. Not of A and B. We call this as, for instance, P, whether you write down it or not, no problem. Not A and B. So it means not A is this column, B is this column. So you are going to AND them. Not A and B. So just AND these two columns to get this. So 1 into 0 is 0. 1 into 1 is 1. 0 into 0 is 0. And 1 into 0 is 0. That's it. Similarly, you go for the next, which is P and, sorry, A and B, which is, let's say you referred it to as Q as well. So next column, A and B. So A and B, you may call this as Q. So A and B. So for this, we have to AND A and B. A and B. Fine. A and B. Just AND these two columns. 0 into 0, 0. 0 into 1, 0. 1 into 0, 0. And 1 into 1 is 1. And finally, you see what is X. X is just P or Q. Fine. So X is what? That is just P or Q. That is just P or Q. I mean, you have to OR these two columns. You have to OR these two columns. Find. So just OR them. So 0 OR with 0 is 0. 1 OR with 0 is 1. 0 OR with 0 is 0. And 0 OR with 1 is 1. So that's it. This is the truth table for the given circuit. That's it. The question is over. But just for the sake of, understanding, let me extend this example. For instance, if you are given the truth table, actually these are the inputs A and B. These are the inputs to the circuit, and this is the final output of the circuit. These are the inputs of the circuit, logic circuit, and this is the final output of the circuit. This one. Fine. This column. Rest of these columns, those we had built while drawing this truth table, and these are the intermediate steps. if, for instance, some truth table is given to you, in that case, these intermediary steps will not be given to you. Fine. These intermediary steps will not be given to you. You will be given the inputs and the output of the circuit. So suppose you are asked to build the logic expression from this truth table. So very important to see that you have to just see where the outputs are 1. These are at 2 places. One is at this place and other one is at this place. I'm going to go back. I'm going to backtrack it from the truth table if I have to build the logic expression. So just going to show you the concept, which is not, I mean, the example is over, but just going to build another concept that if you are given truth table, or to write down the logic expression from that truth table, you just have to see the output column where output is 1. It is in these 2 rows. And then look at the input entries for those. For instance, against this, A is 0 and B is 1. So where variable is 0, just not it. So it is like not of A, and where variable is 1, just without going to invert it, and then do the product of these two. I mean, in between, you have to AND, fine. And then the second is B. So the sub-expression against this one will be generated from here, which is not of A and B. Against every one in the output column, just build one product term. I mean, connected with AND, one product term in such a way that if variable is 0, just not that, like not of A, and if variable is 1, just use as it is, I mean B. So this sub expression will be against this one. And similarly, you can develop sub expression against this one. And this is where both A and B are 1. So product term will be built connecting input variables with AND, fine, with AND, and then this is A and this is B. So the sub expression against this one is this, and then we have to do what? We have to OR these two sub expression, and that is the logic expression. If you are given truth table, and from truth table you're supposed to build the logic expression, that is very simple. Just look at every row where out is 1, build a product term against that from the input combinations, and then OR them, and that is the logic expression. That is how you write down the logic expression. That's it. So this concept will be used in the later on examples. Fine. Okay, move to the next. Let's say over here we are given some logic expression, and from logic expression you are supposed to design logic circuit and the truth table. So let's say the logic expression given to you is x is equal to not of A and B, or with A and B. For the sake of simplicity, I had taken the same example as in the previous case, but over there you were given the logic circuit, and from that logic circuit, you build the logic expression, which was this. I have taken the same logic expression in this case so that you can quickly do this. And you can now see the concept that how from logic expression you have to draw the logic circuit or draw the truth table. Fine. So first of all, we are going to draw the logic circuit from this logic expression. So very simple. Look at what are the variables which are required. Those are A and B. So one is A, and the other one that required is, for instance, B. So first build this sub expression. which is not of A. Not of A is very simple. This is not of A. Fine. And B. B is this. So you do what? You have to and them. So this is this sub-expression which you have built over here. Second sub-expression is A and B. You can tap A from here and B from here, and then you have to AND them. So this is A and B. So this sub-expression is, in fact, it is here. And then what you have to do? You have to OR them. So you have to just OR them. So this is this whole logic expression. Output is X, and that's it. I hope it is clear. Fine. And now the next thing that is asked is the truth table. So you can draw the truth table from this logic circuit or from here. You had already seen how to draw the truth table from the logic expression. So quickly you can see this, the truth table for this. Inputs A and B, 4 combinations, 0, 0, 0, 1, 1, 0, 1, 1. Then you have to build not of A column for this. Then you have to build the column for this, which is not of A and B, not of A and B, and then another column for A and B, A and B. You may call this as P and this is Q. I mean, this is P and this is Q. Then X is P or Q. So this is X is P or Q. That's it. So now you can quickly go through, although you have done previously. So you can see from there as well. So not of A is just inversion of this, 1, 1, 0, 0. And this is not of A and with B, not of A and with B. So just ending of these two columns. So 0 into 1, 0, 1 into 1, 1, 0 into 0, 0, 1 into 0, 0. Then this column, A and B. For that, you have to AND these two columns, A and B. So 0 into 0, 0, 0 into 1, 0, 1 into 0 is 0, and 1 into 1 is 1. And then X is P or Q. I mean, you have to OR these two columns. Fine. P or Q. This is X. So 0 OR with 0 is 0, 1 OR with 0 is 1, 0 OR with 0 is 0, and 0 OR with 1 is 1. And that's it. Fine. Move to the next example. And here in the third scenario, you may be given the truth table, and from truth table, you are supposed to draw the logic expression or logic circuit. Fine. So I have taken the same truth table which we built in the previous two examples. Fine. But this time we are going to build logic expression from truth table. Fine. So let's say this truth table is given to you, and you are supposed to write down the logic expression and then draw the logic circuit. So as I had told you earlier, that if you are given truth table, so this is the output, these are the inputs. So look at the output column where output is 1. This is in these two rows, and then build what? Build the product terms from the corresponding inputs. Fine. So this is, since A is 0, so it is, you have to not it. So not of A, and B is, since B is 1, so you can write down B directly. So against this one, the product term generated is this one. Similarly, do for this row where A is 1 and B is 1. So A and B, and that's it. So this sub-expression against this one, this sub-expression against this one, and then you have to just OR these. So X is what? This, or with this. That's it. And once you know how to write down the expression, logic expression from the truth table. Next thing is to draw, the logic circuit. So logic circuit from this expression, this we had seen earlier as well. So I hope you can do this at your own. Fine. Okay, so move to the next example. And here we are given some problem statement. And the statement is, sometimes questions may be given like this. You're given some statement, and from that statement, you have to build the logic expression, followed by some logic circuit, or maybe ask even to draw the truth table. Fine. So let's read this statement. It is said that a safety system uses two inputs to a logic circuit: an alarm X, which is output, sounds if input A represents off and B represents on. This is one condition. Then OR, second condition, from where you can build the second sub-expression. If A represents on and B represents on. So what you do is, if you have to build the logic expression, and it is said produce logic expression, logic circuit, and truth table to show the conditions that cause output X to be 1. So you have to simply write down the expression, logic expression for that. Fine. So you build the logic expression for the first condition, you build the logic expression for the second condition, and connect them through OR. Connect them through OR. So look at this. A represents off. Off mean A is 0 and B is on means 1. So this is AND. So build a product term for this. So A0 means not of A. A0, so not of A. And you have to connect them through AND. I mean, you have to build a product term. B represents on. I mean, B is 1. So B1 means just B. So this is one sub-expression you build from, here. So A0 or A off means not of A. And this AND B represents on means B is 1. So B is unprimed or without not. Similarly, you build expression, sub-expression for the second condition. A represents on means A is 1, on means 1, and B is 1, B is on, and B is 1. So expression for this is A and B, for instance. This B is 1, so A and B. This is sub-expression for this. And then you have to connect them through what? Through OR. So in between, this is OR operator, and that is X. So this is, the logic expression that you built from the problem statement which is given to you. I hope it is clear. And you may see that I had chosen, even in the problem statement, the same problem where the logic expression, this is the same as we had seen in the previous examples. The next thing, it means to build the logic circuit from here. That is fairly simple. You can do it. Okay. And then finally, you can draw the truth table. You had already seen this. Inputs are A and B. Then you have to build the column for not of A. Then you have to build a column for this. You have to build a column for this. Let's say you call this as P, this is Q. And then you have to output X, which is P or Q. So I hope you can draw this logic circuit easily, and you can fill this truth table, column for not of A, column of not of A and B, which is we refer to it as P, for instance. And similarly, column for A and B, we refer to it as Q. And then finally X, which is the final output, which is P or Q. So you can easily build this truth table. I hope this concept is clear. This is the whole chapter. Thank you very much.